In this video, we're going to set up some definitions of parent functions, and these parent functions we're going to use throughout the year. So we're going to develop that encyclopedia of functions here. The first function we have is called a constant function. An example of a constant function that we're going to use is y equals 1. So no matter what, y is equal to 1. If I were to make a table of values for that, I could pick any number I want to for x, but no matter what x I pick, y is always going to be equal to 1. If I were to plot these points, when x is 0, y is 1. When x is 1, y is 1. When x is 2, y is 1. No matter what I plug in for x, my y is always equal to 1. Because of that, I wind up with a nice straight horizontal line. It has arrows on both ends to show it keeps going forever. It's constant, it's never changing. All right, we also need to give some more information about this function. I need to write the domain and range of the next two things I'm asked for. The domain are the possible x values, and the range are the possible y values. So the domain is x, which is left to right. As I look at my function I've drawn here, going left to right, I go forever in either direction. So for my x's, I'm going to say x can be all real numbers. There's nothing that x can't equal. I don't like writing the words all real numbers. Another way I can do that is by writing a curly brackets. I write x. I make a C shape with a line in the middle, and that says is an element of. That's set notation. And then for the real numbers, I draw a capital R and an extra line coming down. And that fancy R means the real numbers. I would close it with another curly bracket. So I would read this expression here, x is an element of the real numbers. That means x can be anything. How about the range? Range is the possible y values, so that goes in the up and down direction. As I look up and down on this graph, the only y I ever have is right here at y equals 1. So my range is just the number 1. I also could write that by saying y equals 1 in the curly brackets. Either way is fine. Okay, we have some more information. The next two things I ask for are the zeros and the x-intercepts. These are the same thing. Remember, my x-axis goes this way, so my zeros or my x-intercepts are where I hit that x-axis. In this graph, if I look along my x-axis, my function never touches it. So I write none for both the zeros and the x-intercept. The y-axis goes up and down. So my y-intercept is where I touch the y-axis. This graph touches the y-axis in one place, at y equals 1. As a coordinate, I would write 0, 1 for my x-y pair. All right, the next two informations are increasing and decreasing. Remember that for increasing and decreasing, I always go from left to right. I'm also going to ask about the end behavior next, which is on the left and on the right. So as I'm looking at my graph here, so as my graph travels from left to right, what's going on here? Am I increasing? If I were increasing, I would need to be going up. I'm not going up. Am I decreasing? To be decreasing, I'd have to be going down. This one's flat. It's a constant function. So this is going to be never for each of these. We'll get back to more of these in a second so you can see ones that actually are increasing or decreasing. And how about the end behavior? The way we're going to write the end behavior is on the left and on the right. On the left is over here. The left, our x value on the way left would be like a negative infinity, and our x value all the way on the right would be like a positive infinity. So we're going to describe on the left with, as x approaches negative infinity, what's y doing? Y approaches what? Well, y is always equal to 1. So I'm going to say y approaches 1. I use arrows for this because I'm not really concerned with whether I equal it or I'm just kind of getting close to it. So either one works fine, but we're going to use arrows for in behavior for approaching. How about on the right? On the right is over here. What's this arrow doing? This arrow is going to the right. It's going towards positive infinity. So I can say as x approaches positive infinity, that's the right, what's y doing? What's the y coordinate of where this arrow is going? Well, it's just stuck at 1 because it's constant. So as x approaches infinity, y approaches 1. You can look at real life models. A constant function is kind of boring in real life. It's something that never changes. Okay, let's scroll down to our next function. This function's equation is y equals x. We call this a linear function. L-I-N-E-A-R, linear. It's called linear because it makes a line. If we don't remember what the graph looks like, we can start by making a table. This function says y is equal to x. So whatever you want to pick and put in for the x, the y you get out is going to be the same thing. If x is negative 3, y is negative 3. If x is negative 2, y is negative 2. And so on down the line. Whatever x equals, y is equal to as well. Because of that, when we plot our points, I usually start plotting at 0, 0. Right at the origin, that's my anchor point. I started 0, 0. Then I went 1, 1. 2, 2, 3, 3, or I could have gone negative, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3. This makes a nice straight line. The slope of my line is 1. I put arrows on both ends to show that I keep going forever. So, in terms of domain and range, the domain is what's going on from left to right, or what x can equal. In my function, from my anchor point where I started, do I go to the right and do I go to the left? Yes, I do. So my domain is everything. Again, I will write that as x is an element of the real numbers. The range is the y values, or the up and down. From my anchor or origin point, do I go up? Yes. Do I go down? Yes. So if I thought of this like a grid right in the middle, do I go up, down, left, and right? I go everywhere. So y is also an element of the real numbers. Both x and y can equal anything. The zeros for this function are the x-intercepts. If I'm going to look at where this thing hits the x-axis, it's right here at the origin, which is the same place that it hits the y-axis. Now when I write the 0, I'll usually write x equals 0 versus the x-intercept, which I'll write as a coordinate. You don't have to write it one way or the other, but I typically say x equals for a 0 and coordinates for an x-intercept. Y-intercept I'll also write as a coordinate, and it went right through the origin at 0, 0 for that one. All right, here's a function with something going on as far as increasing and decreasing goes. If I start on the left side of my graph and draw to the right side of my graph, I am going up forever. So I am only increasing. I'm never decreasing. Now I need to describe this with an interval. Whenever I do an increasing or decreasing, it's always an x interval. So I need to say that x is between two numbers where I'm increasing. I'm going to make my symbols less than symbols because that way when I start out, I'll write it down here, the left or the lower is going to be less than the x, which is going to be less than the right. So long as you go from left to right, you can always start with the lower number and then end with the higher number, and your symbols will always go the correct direction. Okay, so from left to right, let's see if I could sort of write some coordinates for where these arrows are going. If I were to say the coordinate, the x value of where this arrow is going, the x value would be all the way to the left forever, so it would be negative infinity. The y value of where this is going would also be negative infinity because it's down, and down is negative infinity. For my other arrow over here, my x value, where is my x going? It's going to the right. To the right is towards positive infinity as an x value. my y value is going up. Up is positive infinity as a y value as well. So I know technically we can't write these coordinates with infinities in them, like we could write 0, 0 or 1, 1. But I want to be sure you realize that when we're writing increasing and decreasing, we're always using the x values of the points. So on the left, my leftmost arrow is at negative infinity. So when I go to write in my interval up here, I'm going to start with a negative infinity. My right value is at positive infinity over here where this right arrow is going. So I say from negative infinity to infinity, this graph is increasing. For the end behavior, that's when I'm writing my as x approaches something, y approaches something. The nice part about writing in these coordinates is that my xy of the coordinates are my xy in my approaching statement. So as x approaches negative infinity, the y partner to that coordinate was a negative infinity. Y approaches negative infinity. Then we'll go to our second coordinate. And again, I'm going to say as x does something, what does y do? Well, let's look at those values. My x value in my pair was a positive infinity, and my y value in my pair was a positive infinity. So both of these are the two ends of my line. Those are the end behaviors. All right, next function in my bank of functions is y equals the absolute value. That's the name for this. And the absolute value is shown by putting these straight bars on the sides of my function. If you remember absolute value from Algebra 1, absolute value makes things positive. So if I'm looking at my table over here, the positive numbers, or 0, the absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. Absolute value doesn't do anything unless you're negative. If you're negative, the absolute value of negative 1 is positive 1. The absolute value of negative 2 is positive 2. The absolute value of negative 3 is positive 3. If you're negative, the absolute value will make you positive. If I were to plot this function, again, I'm going to start at 0, 0 when I graph. The right side of my graph, where both x and y were already positive, the absolute value doesn't do anything to that. It still looks like my straight line. The difference is on the left side. Rather than getting negatives out, if x is negative 1, my y is positive 1. When x is negative 2, my y is positive 2. And if I were to describe this thing, I call this my V shape, because it's nice, sharp V, straight lines on either side, and pointy. The ends both have arrows on them, because I keep going forever to the left and to the right. So let's talk about our domain then. If we're talking left and right, let's start with our anchor point right here. My whole graph started at the origin. From my anchor point, do I go left and right? Yes, I do. So my domain is everything, and x is an element of the reals. From my anchor point, do I go up and down? Well, I go up, but there's nothing in this spot down here. So I have to make a restriction. When I have a restriction, I write y, and then I write a line. That's a such that line. So I'm saying y, but wait a minute, there's some more information. Y has got to be greater than or equal to 0 because I only go up, and up is greater than in the y direction. The y value at this point at the origin was 0, so y goes up from 0. Y is greater than 0, or greater than or equal to 0. Okay, my zeros, or my x-intercept, that happens right here at the origin. So again, for a 0, I'm going to say what x equals 0. Whereas for my x-intercept, I usually write it as coordinates 0, 0. And my y-intercept is the same spot. I hit the y-axis at 0, 0. This one for increasing, decreasing has two things going on. So as I go from left to right, when I start out, what's happening? If I'm going from left to right, I start out and I'm decreasing. So there we are with the decreasing on the left side of the graph. Then I make a sharp turn and I switch, and the right half of my graph was going up. So that part was increasing. Remember, we have to go from left to right. So let's label the arrows and the turning points here, just like I did for my last one. I'm going to try and pretend that there's coordinates for each of these arrows. And I'm also going to put coordinates right here where I turned around. The turnaround point is easy. That was 0, 0. That was my origin. But let's look at this one. This arrow is over here on the left, so its x value is negative infinity. But it's going up, so up is y value of positive infinity. This arrow on the right is going towards x is positive infinity. It's also going up, which means its y value is also positive infinity. So now I'm going to write my intervals for increasing and decreasing. I'll start with increasing because that's the top one on my list. Increasing, remember, is this part here that I did in green. So where am I increasing? I'm increasing from 0 to infinity because I just want the x values. So 0's on the left, infinity's on the right. In the middle is my less than x less than. Remember, the smaller number has to be on the left, bigger number has to be on the right. So now when I go to do my decreasing is this piece right here. My left is negative infinity and my right is 0. When I write them, I have to put the smaller number first and then the larger number. Negative infinity is smaller than 0. So even though my graph is up higher on this left point, going from left to right, I start with negative infinity and end at positive 0. Okay. The end behavior is asking where are the arrows. I have two ends, so I'm going to have as x approaches something, y approaches something else, and then I'm going to have a second arrow, so I'm going to have a second as x approaches something, y approaches something else. You should be able to just sort of fill in those blanks as you're writing. So let's start out over here with this arrow. This arrow on the left, x was negative infinity, so I'm going to fill that in my x spot. Y was positive infinity, so I'm going to fill that in my y spot. As x goes to negative infinity, that means the left. Y goes to positive infinity, that means up. Let's look at my second arrow over here. As x goes to positive infinity, y goes to positive infinity. Positive infinity for x is on the right. Positive infinity for y is up. So as x goes to the right, y goes up. Okay, there's a couple more parents here. The next one is y equals x squared, which is called a quadratic function. Our quadratic function, if we were to square each of these values in our table, starting out, negative 3 squared is positive 9. Negative 2 squared is positive 4. Remember, when you square, you're multiplying by itself, and a negative times a negative is a positive. So 0 squared is 0, 1 squared is 1, 2 times 2 is 4, 3 times 3 is 9. So if I plot these points in my graph, again, I always start with 0, 0, because that's my anchor point. 1 squared is 1, but at the same time, I'm going to go over here and do the same thing on the left. 2 squared was 4, so I'm going to go over 2, up 4, and that's where I'm going to put my next point. I'll mirror it over there on the left. My next point, 3 squared is 9. So I go over 3, up 9 to get to my next point. I could keep going. 4 squared is 16, 5 squared is 25, but I don't need to do that. I erased those intermediary lines, and now I'm just going to make this U shape. This is a nice smooth curve. It bends. It's not pointing like the absolute value. If I were to describe this, I would call it a U shape. It has arrows on both ends to show that it keeps going forever. All right, when I go to do the domain range and all the rest of the information for this, really the basics of this graph are just like the absolute value, that V shape. It has the same domain. It goes left and right forever. It has the same range. It only goes up. It starts out, and if I were doing my increasing and decreasing, I start out on this thing and I decrease on the left side here, and then I switch over and I increase on the right side. So this is going to have all the same information as the absolute value graph. I'm going to just fill that in to save time here. So my domain, x is an element of the reals. My range, y, such that y is greater than or equal to 0. My 0 is at x equals 0. My x-intercept 0, 0. My y-intercept is 0, 0. I'm increasing on the green section down there, which started at 0 and went to infinity. I'm decreasing on the pink section, which started at negative infinity and went to 0. My end behavior for my two ends, I had as x went to negative infinity, that was the left, y went to positive infinity, which was up. And as x went to positive infinity, which was the right, y also went to positive infinity, which was up. All right, we've got one last function here to deal with, and that is our square root function. And we're going to call it just that. We're going to call it the square root. On my square root function, I have something weird when I go to plug my numbers into my table. If I go to take the square root of -3, I can't do that. I can't take the square root of -2 or the square root of -1 because those numbers don't exist in the real number system. We'll deal with what they are later. Square root of 0 is 0. Square root of 1 is 1. Square root of 2 is yucky. It's 1 point something. I'm just not going to want to plot that point because it's not a nice grid mark. I don't really like the square root of 3 either because it's 1 point something. It exists, but I don't want to find it. What else could I take the square root of? I like the square root of 4. That's 2. I don't like the square root of 5 or 6 or 7 or 8. I like the square root of 9 because that's 3. So the points that I'm going to plot for this one are the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So plotting those on my graph, what I wind up with is half of a U shape pointed sideways instead of going up and down. It has a solid endpoint on the origin and an arrow on the right to show that it keeps going that way forever. All right, let's do the domain and range. Starting my graph right here at the beginning, this is the first one that when I ask, does it go left and right, I have an answer of no. This graph only goes to the right. So just like with my domain, with my range, I'm going to have a domain restriction. So I'm going to say X, and I'm going to put a line to say, whoops, there's more information. What happens here? X only goes to the right. The right is a greater direction, so X is greater than or equal to 0. This point, remember here, my origin is 0, 0. For my Y, do I go up and down forever? No, I only go up. So I have a restriction of Y being greater than or equal to 0. For the zeros in the x-intercept, again, still at the origin, so I have x equals 0 and 0, 0 for both my x and y-intercept. For increasing and decreasing on this one, I only have one part. I can't go all the way to the left. My whole graph starts right here. I only go to the right, and I'm going up the whole time. So I'm only increasing. I'm never decreasing. I'm going to write never here for decreasing. So let's put the coordinates of the ends. Well, I already have the coordinates of the left end. That was 0, 0, the origin. My right end, as x goes to the right, that's a positive infinity. The y is going up, which means y is also positive. So I'm increasing. I need to write the two x values. The first x value is 0. The ending x value is infinity. So I have 0 is less than x, which is less than infinity. When I go to do the end behavior, I need to do the x and y values of each ordered pair. So my first ordered pair was at 0, 0. I can write as x approaches 0, y approaches 0. For my second endpoint, I have infinity, infinity. as x approaches infinity, y approaches infinity. I just want to point out that if there was a question on here that said, as x approaches negative infinity, y approaches blank, and you were to fill in that blank, what would you put there? As x goes to negative infinity, that's way over here on the left. Does x go to negative infinity? No, it doesn't. So you just put not applicable. That doesn't work. We can't do a left end going to negative infinity because the left end stops right here at 0, 0.